Hello and welcome to section 3 of interactive chatbots using TensorFlow. In this section, we will dive into deep learning and neural networks and learn how to integrate them into our pipeline. In the first video, we are going to learn about linear models. Linear models are models that depend on a linear equation to solve their tasks. Let's see an experiment to illustrate that. First, we import the needed packages, which are NumPy, Matplotlib, and some scikit-learn modules. Next, we create a classification dataset and visualize it. As you can see, we have two classes, the red class and the blue class. These two classes can be separated by a line passing through this area. We train a logistic regression model. A logistic regression model is a linear classifier. A classifier is intended to separate two classes from each other, as we can see in this area. We train a logistic regression model and evaluate it, and visualize its decision boundary. The decision boundary is the line that the model draws in order to separate the two classes from each other. We can see that from the evaluation of the model that it has solved the problem by 0.98 accuracy or precision. The overall score, which is the F1 score, is 0.98. The F1 score is an evaluation metric that we use to combine precision and recall. Precision and recall are two evaluation metrics we use in classification. Precision and recall can be tricky. The intuition behind precision is that whenever a model predicts a certain class, for example class 1, it is 98% correct. Recall is the proportion of actual positives that were identified correctly. In other words, how many instances of the class, for example the blue class, were identified by the classifier. What we have here is called a classification report. In a classification report, we have our classes, which are 0 and 1, the support, which is the count of examples from each class, and certain metrics like precision, recall, and F-score. F-score for class 0 is 0.98, F-score for class 1 is 0.98, and the average F-score. The same can be said for precision and recall. The test set accuracy is the same, but for a different set, which is a held out set that we use for evaluation. Logistic regression fits a line in a space that can be able to separate the two classes from each other. In other words, the line will be able to tell us which area belongs to the red class and which area belongs to the blue class. That works well in this dataset because it is linearly separable. Let's create another dataset and visualize it. In this dataset, we can see that the two classes are entwined. In other words, there is no line that can separate these two classes perfectly. We train a logistic regression model and plot its decision boundaries. As you can see, the line fails miserably to separate the red class from the blue class. The performance of the model degrades, as you can see, from 0.98 to 0.76, and on the test data to 0.82. In the previous dataset, it performed on a test dataset by 0.96. That shows a huge degradation in performance. This is because the data is not separable by a line.